Alright, so today we're going to take a look at Newton's third law of motion. So go ahead and we can define it on this slide here. Sorry about that. And that is Newton's third law of motion is whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction of the force it exerts. So going through here, this slide, I went ahead and talked about what was going on here. So a very unique thing that happens with baseball is that the pitch known as a cutter, whenever Mariano Rivera, who pitched for the Yankees for a long time, threw his cutter, the ball and the bat would frequently come together at a specific point on the bat that would actually end up shattering the bat more than the average pitch would do. Pretty cool little thing that happens there, but people usually think of it as the ball's breaking the bat, but it's also the bat is also putting a force on the ball as well. And so because of that, baseball analysts now look at exit velocity as a key statistic as well as just how fast pitches are coming in. So here's a quick question, Newton's third law, again, the definition of it. And so A here says the body remains at rest, or if in motion, remains in motion at constant velocity unless acted upon by a net external force. That is Newton's first law. B says the rate of change of momentum of a body is directly proportional to the applied force in the direction of the force. That's on the way to being Newton's second law, but momentum is not Newton's second law. It's the acceleration is directly proportional to the force being applied. So that's actually talking about momentum and what's called impulse, but we'll talk about that in a couple of units. Every action has equal and opposite reactions. That is Newton's third law. Every action is equal and same reaction. That is just changing one word in Newton's third law, trying to trick us. So Newton's third law is known as the action-reaction law. So, like every action has an equal and opposite reaction. Right? That's the very general form of it. And this talks about how swimmers push off of the pool, but it does have some typos in it. So we're going to go ahead and take a look at the picture that goes along with this. So here we have a swimmer in a pool, and you can see she is pushing off the wall. The wall is pushing onto her feet as well. But the main thing we want to look at, the system of interest here, is the swimmer herself, not the wall and the swimmer, because if we just look at the wall and the swimmer, then our net force is zero. There's no, the forces that are going on there counteract each other. But if we look at the system of interest as just the swimmer, then we have this free body diagram to the right here that has the wall on the feet, the weight of the swimmer, and the buoyant force keeping her in the water where she is. And so her acceleration is to the left, and that's the direction of the force as well. Newton's third law also tells us that forces occur in pairs. So explaining how the system of interest affects whether pairs are going to cancel, well, if we look at that last problem, if we include pairs that are going to cancel each other out, we might be canceling something that is important to the problem. So that's why choosing the correct system of interest is very important, because if you overdo it, you pick too much of what's going on, then you might be missing, or you might be adding in things that are going to cancel each other out. Or if you go the other way, you might be ignoring forces that do apply to the system that you need to be looking at. So it just depends on the problem as far as how much is going on in that problem. So thrust is a good example of Newton's third law. And really it actually works a different way than most people think. So I'm going to go ahead and highlight one part here I do want you to write down about thrust. So the rocket exerts a large backward force on the gas in the combustion chamber, and the gas therefore exerts a large reaction force on the rocket. And that's how thrust works. So most people think that it's something shooting out of the rocket that's pushing on the air or the ground outside of the rocket, and that's what makes it propel itself. But it's really not that. It's what's occurring in the Ooh. Pardon me. In the gas chamber itself, the explosion per se that's going on inside of the gas chamber that's pushing the gas out, and then that push is also has an equal and opposite push that's pushing onto the rocket going the other direction, and that is what is pushing the rocket forward, not the other way around. There's a couple more examples there listed too. Helicopters create lift, planes create lift in a certain specific way that also push up. So lift is called that because it lifts things up, right? So helicopters work a little bit differently, but they do still create that same lift that pushes the air down, and the air pushing down therefore has an equal and opposite reaction that pushes the helicopter up. Or planes, for example, flying through the air, as well as birds, their wings cause lift and forward motion as well, the same way. And there's also another example here. I didn't even know this one until I read this, that an octopus actually propels itself in the water by ejecting water through a funnel in its body, similar to a jet ski. That's how jet skis work too, if you didn't know that. But I didn't know that octopi did that. I always thought they just used their tentacles to move themselves around or to propel themselves through the water like a human swimmer does with their hands. But turns out, no, pretty cool. So we're going to skip over this, going to skip through some things just to make this video kind of short. And that last problem, we can talk about it, but really explaining why you move backward in your seat, well, it's twofold, right? Not everybody leans as far back into their seat as they possibly can, and even then you still feel a little bit of a push into the plane seat whenever you are taking off, and that's just because your body wants to remain at rest, and so it tries to do that, and then it pushes into the seat as the plane moves forward, so that there isn't really a backward force propelling you, but the plane's forward force then applies a bit of a backward force, but it's like it's not the same way in other ways forces work, because we're not in contact with it, right? It's really just that our bodies want to stay at rest, and the plane's not. Here, ordinary rifles. I'm not a weapons expert here, but obviously, so the barrel of a rifle is closed at the end, and whenever the bullet, for lack of a better term, explodes inside, it propels the bullet forward, but the shell pushes back on you, and that's where recoil comes in. I didn't even know recoilless rifles existed, so I couldn't really speak to that, but I'm assuming that since the barrel is open, that leaves there space for the shell to come back out, and that way you don't have that recoil. Now, whether or not you can stand close behind one, I would say probably less likely to stand behind one, or safe to be standing behind one, because there's shells flying out more. So I would probably say you don't want to, more than a regular rifle. I'm not sure though. So again, not a weapons expert. So all right. So this problem here, we are going to do some calculations here. We have a professor pushing a cart with some equipment on it, and there's a whole bunch of info given on to us here. We're going to come back to this slide to do the calculations, but we're going to look at this picture first. So here we have the picture of what's going on. You can see the professor pushing on the ground with her feet, and she's pushing this cart has a mass, and all the stuff on it has a mass. We have all the info for all of that on that last slide. We can see the free body diagrams going on here too. So for our first part of this problem, then what we want to find here is we want to find, asked for it here. Yeah, the acceleration produced by the professor when she exerts a backward force on the floor. So we know the force she's applying. We just need to figure out the force that is our net force, and then use that to find the acceleration going on here. So we need to pick the right system. So we have system 1, which is everything, the professor in the cart, and since the professor is her feet are what we're looking at, we need to include her in it, so we can't just use system 2 because that doesn't include the professor's foot to floor contact. So we are indeed going to have to use system 1 here. So you can see the forces that are acting there. Free body diagram is there as well. We're going to go ahead and draw that on this slide as well. So give me just a second to take a screenshot. Can't write on these ones. So we have our highlighter. Give me a second to fix that too. All right. So we have our free body diagram here again. This is the friction. This is the force the professor is applying. We have our normal force, and we have our weights. Now, normal force and weight are going to counteract each other, so we don't really need to worry about those too much, but we do have two other forces. So again, net force, as always, is equal to mass times acceleration, Newton's second law. And then in this case, our net force is going to be the professor's force, Fp, because that's going off to the right, minus our frictional force that is counteracting it. That's straight marks here. Let me clear those out. So we can go ahead and set these equal to each other because they are both the net force. But before we do that, let's list out everything we do know here. We have our backward force, Fp, is 150. We have the frictional force, or the air resistance and frictional force altogether, is 24 newtons. Make sure we include our units there. And then we also have that the mass. Now we're including everything together, so that's the cart, the professor, and the stuff on the cart. So that's going to be 65 plus 12 plus 7, which comes out to be 84 kilograms. And we're looking for acceleration. So we have everything else except for the mass. So when we set these equal to each other, or except for the acceleration, sorry. So equal to Fp minus our frictional force. And so we're going to go ahead and plug everything in. So 84A equal to 150 minus 24. You want to do that subtraction. So 84A equal to 126. And now we're ready to go ahead and divide to get A all by itself. So dividing by 84 gives us our acceleration, which is 1.5 meters per second squared. And you can go ahead and look at what they do. It's the same process. They added all the masses up, got 84. Now they go ahead and have the net force separated out instead of setting the two net forces equal to each other. I like to just set them equal to each other. It's a bit better of a system in my head, but whatever works for you. But there's how they solved it. So now we have this next problem. We're going to skip this one because we're actually going to do a very similar actual problem where we actually have to calculate. This one doesn't tell us anything numbers wise, so we'll do that one here in a minute. So now looking at the professor again, this time though we want to know the force that the professor exerts, so we want to find that Fp in the middle. Probably should have labeled that last one FF or whatever for the force of the floor, but that's okay. So this one's really the Fp that we're looking for. So now we're looking at system 2. Alright, so for this problem here, we're looking at just the force that the professor is putting onto the cart now. So that means we can switch the system up to looking at system 2 only. Because we don't need to deal with the forces from the floor, except for what we got earlier, the acceleration that she's using is going to help us because that's going to be the acceleration going with the cart too, because all in all, it is one overall system, and that acceleration applies to that cart as well as the professor. So I'm going to go ahead and change to this screen here. more space. But all the numbers that we had on that previous set still apply here. So I'm going to go ahead and draw our free body diagram again. So our frictional force still acting that way. We now have this force of the professor, and still have a normal force, still have the weight, still those two are counteracting each other. Our net force, as always, is still mass times acceleration, but now our mass is actually just the cart, which was 19, and the stuff on the cart, which was 7, and so that's going to be 26 kilograms. Oh wait, sorry, I have the numbers wrong there. Somebody walked in earlier and I had to restart the video recording. Now I forgot all the numbers. It's 12 plus 7 equal to 19. I knew the numbers didn't seem right. There we go. And so then we have our net force is, of course, equal to the force the professor is applying minus our frictional force again. But now this time our FP is what we're looking for. Our frictional force is still the 24 newtons. And now, though, the acceleration is 1.5 meters per second squared, what we got earlier on the previous problem. So we have everything again we need. Set these two equal to each other. Mass times acceleration is equal to FP minus the frictional force. Our mass is 19 kilograms times 1.5, and it's going to be equal to FP minus 24. So 19 times 1.5 is 28.5. And we just need to add 24 to both sides. That's going to give our force of the professor is going to be 52.5 newtons. So again, looking at their work, they have the same process that we just did, just a little bit different. I don't know where they got the bottom stuff from. 8 kilograms, I don't know where that came from, let alone the 126 divided by 8 is definitely not 1.5. But we know where they got the 126 from. They just took that from the 150 from before. But I don't know where we know where the 1.5 came from. That's from the previous problem. So there we go, multiplying that out. They did go ahead and round as well. So they got 29 and then 53. But same idea for us, just 0.5 off because we did not round. All right, so this next problem, this is the problem I was referring to earlier when we said we were going to work through another problem similar to, actually, I don't want that screenshot, similar to the football player. I want to make sure I can see all the work here. So I can't see all of part C there, but part C is just continuing on what we're talking about, drawing a sketch, and we're going to do that through the process of parts A and B anyway. So for part A, we have a rugby player who is getting a force of 800 newtons exerted onto him. So that's kind of like the force the professor is putting on the cart before. So we'll even call that FP, because that's the force of the player. The mass of the losing player, so our mass here is 90 kilograms. So this one, we're actually going to be working a little bit backwards from what we did before, because we are now looking for A was the force of friction, so we're looking for that frictional force. So we're going to focus on the smaller player first. So drawing a picture here, we have a larger player and a smaller player, and this guy's putting a force FP You have the frictional force acting this way, and of course they have their weight and normal forces. But the system we are interested in is really just the individual player. So free body diagram of this situation, we have the player, force of the player 800 newtons that way, the frictional force this way, normal force, and weight. So again, that's our FP. We're looking for that frictional force. Our net force, of course, as always, is mass times acceleration, and then our net force in this case is going to be FP minus the frictional force again. And in this case, we have mass, we have acceleration, we have the force of the player. We're looking for the frictional force. So FP minus the frictional force is equal to MA. So 800 minus the frictional force is equal to 90 times 1.2. So that's going to be 800 minus the frictional force equal to 108. I'm going to subtract 800 from both sides. That's a negative 692. But we have that the negative frictional force is equal to negative 692, so our frictional force is 692 newtons. Now, part B, let's just do something similar. The force, we want to know what the force the winning player is putting on the ground. So now, same picture for the most part. But we're going to call that FF down the bottom there. And of course, FG, FN. In this case, we were looking at the overall system. So FP is actually getting counteracted there. So the force that the bigger player is putting on the ground is what's causing the movement here. So you have our system. We have this FF, the frictional force, normal force. So then our weight. And so now, again, we have everything here except for FF. That's what we're looking for. The frictional force we just got is 692. Our acceleration is still the 1.2, but now our mass is actually both of them combined together, so 90 plus 110, so 200 kilograms. Net force, mass times acceleration, and then our net force is FF minus the frictional force. So FF minus the frictional force is equal to mass times acceleration. So that's going to be 692 there, equal to 200 times 1.2. That's 240. So we just got to add 692 to both sides. We've got our answer. .932 newtons. So again, we already answered part C, and by doing that, we did the free body diagram and drew the pictures and wrote out the net force equations and all that throughout the process of doing parts A and B. The rest of the notes are a FET simulation, which doesn't really even go with Newton's third law, in my opinion. It's more for Newton's law of gravitation, which we'll see next unit, and the exit ticket. So that's it. Catch you next time.